right, for those who joined us late, we've been trying to get the recorder to start, and it's been giving problems till now. I'm in Blackboard, this course, Math 1, 227, handouts, PPTs, and more, and we're going to go to the bottom down here. There's all the PowerPoints. Here's the one where the Math YouTube videos are. The rest of those are other sites you can go to and get maybe more help if you want, looking for it. So click on YouTube videos, and you get, waiting for this, it's getting into YouTube. Connecting. Okay, here we go. The ones at the very top here are the oldest ones out there. And I don't know what term I did it, but then there have been some terms when we did things like started as early as 8.3. Well, we didn't this term. We started more in a reasonable place. So all these at the top are the very oldest ones out there, okay? And so sort of ignore most of those until you get down here to, and this is that should be a 13.3 and 4. So there are a few typos and stuff like that in here that you'll see. Don't let them swamp you. This is where our course begins. Math 1, 227 syllabus. That's this term. And then we did the syllabus, all the things we did at the beginning. We even got started in 11.5. That's where you wanted to start. There was when we finished 11.5 and started 11.6. Now this one, I don't know. That's supposed to be 11.5 through 6. I guess type 5 through 6. That's just an error on my part. That's 11.5 and 6. This is when we finished 11.6, and there's when we did 11.7. Did the quick run through of that, and 12.1. And that's where we left off last time. So these from these here through that was, when did we start? On Wednesday or Monday? That was a Monday, Wednesday. We didn't have class last. Yeah. 227, yeah. Monday, Wednesday. That's right, because last week was Labor Day. So, yeah, those are all the classes we've had this term. The ones up above it were from previous terms, and as I do things here, and like today we're starting in 12.1 and going to maybe getting to 12.2, well, if somewhere up here there's a 12.1 and 12.2, looks like there's not. I don't know why there wouldn't be. I must have already deleted it by mistake. Okay. So I must have already deleted the 12.1 to 12.2. Shouldn't have, but I must have. Right there. It seems like it starts. That's probably 12.2 to 3 there, not 3 to 3. Sometimes my typing is really poor. But these are the ones. Now, is one of these one that you can't get to open? Which ones have you tried to open? Any of them?
Yeah, those probably, the other ones are on there, but I was starting the 227 syllabus, I can't get it.
This one right here, this one that says syllabus?
Yeah.
That one right there.
It's the star, but I can't get it.
Okay, let me see if it may not have, just like you saw, it was screwing up today, so it may not have recorded well. Boy, this takes a lot longer than I thought it would. Of course, I don't go back and listen to them, so that's why there could be some duds out there, and I wouldn't know it because I hate listening to myself. Okay, and boy, this is still up, I'm not sure. Let's minimize that. So
and we'll start with the syllabus today. I'll tell you right now, it's
do you
not
get any
updated.
of this?
This was last summer's
No, okay.
syllabus.
Check
for
with
the
her then,
course.
because
The course
it's out
stuff
there. I
is
wanted to
correct.
make sure if you went down there, it was indeed
Points are
there.
not,
So,
because number one,
okay.
I wasn't sure if they're going to
So I'm going to,
students only to pay.
what?
They may
How
still
do you
not,
stop this
but
thing? I'm just
hopefully
going to stop it
they
this
will.
way. Okay. All right. I just wanted to make sure that the one you were listening at actually worked. And it did here, so it must be something. You brought your laptop or whatever? Yeah, good. Okay. She's good. I haven't seen her today, but I think I saw her vehicle here. So anyway, let's get out of this. I am recording. Have I got the PowerPoint open? No. I must have closed it by mistake. Okay. No, I didn't close it by mistake. I did it by intent. Okay. 12.1, limits and continuity. That's where we are. Let's start the slideshow from there, even though we've had the recorder going for a while. We haven't started. Okay. Any questions? Anything we've done up till now? And as I was telling my last class, this was in my box this morning. They pass them out just about every year. Dick Coffey, I have no idea who Dick Coffey is, but this is Dick Coffey's Football Guide 2019. If any of you are interested, has a picture of Tua Tagovailoa, whatever, from the quarterback for Alabama with Nick Saban's picture, and then Derek Brown, who I don't know what position he plays, defensive maybe or something, and Gus Malzahn. This is a 69th edition, and it has all sorts of stuff in it. That's the first few times I've ever opened the thing. So if you want it, it's here. If not, it's going to be here until someone picks it up or it gets thrown away. So if you want it, it's there. All right, that's the only other. Oh, one other. This is sort of a minor one. Most of the time on Mondays, I'm here till 6. However, today at Sloss Furnace, way back, I don't remember when it was. Hopefully, you'll find out today. You know, that was a active mine say again.
Furnace. Active furnace.
Furnace, yeah, that did steel, made steel and stuff like that. And of course, this was Jim Crow era, and worse. And a lot of the laborers were blacks, and for some reason, I don't remember the whole story of it, they lynched, I think, 1 or 2 people there. And they're putting up a memorial plaque because it seems as our history never mentions that part of the history. So there are groups that are trying to get that also part of the history story, So there is a memorial plaque going up there. The ceremony begins at 6 today, and since I usually stay here till 6, I'm going to leave about 5:15 so I can try to get to Sloss Furnace in time for that unveiling or whatever it's called. My wife knows all the details, and she told me about it. She said, but you're not going to get there in time. I said, well, I'll try. So anyway, not a very pretty part of history, but it's still part of the history. All right. Any questions before we get started? All right. Limits and continuity, of course, 2 of our favorite subjects of all time. We're in Chapter 12, Vector Value Functions. We're going to be looking at limits and continuity of vector value functions. So here's the definition of the limit of a vector value function. If R is a vector, notice bold is R here. I can't draw bold, so when I write it, I put the arrow over it. If R is a vector value function such that R of t is some f of ti plus g of tj. Now this is in 2 dimensions. 3 dimensions we're going to do down here. Then the limit, this is the limit of it. Limit as t approaches a of R of t, vector R, would be the limit as t approaches a of f of ti plus the limit as t approaches a of g of tj. Notice these are scalar functions. F and g are scalar functions. R is a vector function, but as the t approaches a here, that's when t approaches a for the f part, t approaches a for the g part, and those are the I and j components of it, provided that f and g have limits at t as t approaches a. If they don't, then r doesn't either. Okay, so don't even try. Now, if it's in free space, f of ti, g of tj plus h of tk, then the limit is r as t approaches a of r of t would be the limit as t approaches a of f of ti, g of tj, h of tk, provided f, g, and h all have limits as t approaches. These are in the plane, these are in space. So the limits, hopefully, are exactly what you expect them to be, and indeed they are. Nothing new, big, nothing you have to fiddle with just because they're vector functions. Just basically plug it in, okay? So, if r is approaching the vector L, here's your r vector here, and it's following this path here and is approaching the vector L here. Here it's a long old vector here, it gets a little longer, then starts shortening up, approaching L, okay? Then the length of the vector r of t minus L, this is r of t, there's L, so r of t minus L, that would be putting L down here, putting that at the end here, then this vector would be exactly this vector here. This is r of t minus L is approaching 0. Of course, if r is getting closer and closer to L, r of t minus L is getting shorter and shorter and shorter, and it's approaching 0 as t approaches a. Now, where did that go? Oh, if r of t approaches L as t approaches a. So r of t is ultimately approaching L as t gets closer and closer to a. So that means L is r of a. That's what they're getting at here. And this is showing this, what I was doing with my hand, they're showing here. As t approaches a, r of t approaches the limit L. For that limit L to exist, it's not necessary that r of a be defined or even equal to L. That's just what it's approaching. Because r of a may be defined some other way, but this, if the limit is that, then as this gets closer and closer, see here, that difference is here, there, there, as it gets closer and closer, as t approaches a, the r of t gets closer and closer to this limit L. Whether or not it's even defined there or equal to that there. Because you can, if you remember, you can have weird things happening at any point, and it may not have that same value, but that's its limit. So the next definition extends the notion of continuity to vector value functions. A vector value function r is continuous at the point given by t is equal to a when the limit as r approaches t exists as t approaches a. So first the limit has to exist, and the limit has to be as t approaches a of r of t would be r of a. Remember back what we said before, the limit may exist, but it may not be that value. For continuity to be true, it has to be that value. R must be defined to a, and it must be, that limit as t approaches a must be r of a. The vector value function r is continuous on an interval I when it's continuous to every point on the interval. That means there's no holes, no gaps, no breaks, or anything else. They're all there. The limit can exist even if the function isn't defined there, if that's just what it's heading toward. Or even if the function at that point happens to be up here somewhere, but the limit is still going to that point there. Okay? This says for it to be continuous, that r of a must be that limit, must be the end point. Okay. Here's example 5. Discuss the continuity of the vector value function r of t equal ti plus aj plus a squared minus t squared k, where a is just some arbitrary constant at t is equal to 0. Okay? So, when Oh, I got to get my pen set up. Okay. When in doubt, you just plug in the value here. What is R of 0? What would that be? 0i plus aj
a squared minus 0
k. A squared k. All right. Discuss the continuity of the vector value function there at t is equal to 0. The only thing that might give us a little issue, let's just make sure, if we were to factor this to be a plus t times a minus t, as t approaches 0, that's still a squared. So yeah, there's no issues going to come up there either. So that's what it is. Now, discuss the continuity there. I don't know really what they're getting at, except there is no I component. That has an I component everywhere except t equals 0. So there the I component goes to 0. The A doesn't change at all, so you're just coming down. See if we can picture this. If that's the x-axis, this is the y-axis. The y component of this vector r is always going to be a on y. You know, a units out on y. We'll just assume they're positive so we can see them here. And then a squared minus t squared j, well, as it approaches t at t equals 0, the x component, whatever it was, has been getting less and less and less until it's disappeared. You're still at aj, always was aj, and the a squared minus t squared, if t was larger, then that could have been a negative number for a while, and then it comes up when the a is equal to, or t is equal to a, it's gone to 0 on the k component, and then as t continues and goes to 0, then this is going to a squared on k. So wherever a squared is up here, so that would be the point here. If this is a, let's choose this to be a and this to be a squared. So the x component has come in like this. T, if it's decreasing going to 0, it's come in like this. The y component could have started negative, or something that went to 0 when t was equal. No, the y component was a always. Sorry, it was a always. It was always here. So it's been coming in like this, coming in like this. Okay, it's 0 here, and the z component could have been negative down there, negative coming up when t is equal to a. It was 0, so wherever that was, and then it's coming up till it goes to a squared. And on z, this is a squared. So this is coming to the point. So I don't know what they mean by discussing the continuity, but it is continuous there because it's defined there. Let's see what they are doing with it. As t approaches 0, the limit is t approaches 0 of r of t would be r of 0 equal to limit as t approaches 0 of t, that would be 0i, which is exactly what we did. Limit approaches 0 of a, that's just going to be aj, exactly what we did. And the limit as t approaches 0 of a squared minus 0 squared would just be a squared. Yeah, that's it. I guess that's all the discussion you need. I don't know. Discuss the, well, let's see if they say something else. That's aj plus a squared to k. I guess that was in the discussion. No, here it is. because r of 0 is equal to that, you can conclude that r is continuous at t is equal to 0. Yeah, and that's all my arm waving, that's what I was getting at. It's coming closer and closer to that and terminating there, so it is continuous at t equals 0 because it's defined there. Okay, it has meaning there and no gaps getting there. Okay, yeah.
Yeah, is this just, he just threw that out. He's not saying where this function came from. So, okay, this is just like, we're going to say 10 plus 3 is equal to 13.
Yeah.
Is that what he's saying?
Yeah, that's all I can figure that he's saying, yeah. This gets there, and it gets there, and since it's defined there, and, you know, notice back what the thing said. A vector value function is continuous at the point given by that when the limit exists, and ours did, and the limit is that value, r of 0. And it's both of those things, so it's continuous there. All right. By similar reasoning, you can conclude that the vector valued function r is 0 at all real number values of t. And that's what my arm waving was trying to show, that it's coming in this way from here. It's always that way on y, and it's going from wherever it's coming from. But yeah, it's continuous everywhere because nowhere did that form that we originally had fail to exist. Okay? That exists everywhere. They're polynomial functions. Polynomial functions are continuous everywhere. Now, if you had had the square root of a t in there, hey, they are not continuous at negative t's. Okay? If you had had something over t in there, oops, okay, whatever is over that part couldn't be 0. Or the log of something with t in it, that can't be 0 or negative. But these are polynomials that are continuous everywhere. R of t is continuous everywhere. Okay. Because each of the component functions is continuous everywhere. All right, is this the same problem? Or so? Yeah, I guess so. For each value of a, the curve represented by the vector valued function in example 5, that's the one we were just working on, wasn't it? Oops, I hadn't even turned the page. Yeah. Yeah. Is a parabola. Okay, here's, I couldn't find my x-axis here. There's the x-axis down there. The y is always equal to 4. Is always equal to a. I'm trying to see where they represent that here. Oh, yeah. They say a is a constant and then they let it vary. Okay, so that's what the problem is here. When a is equal to 0, you have t I minus t squared k, and that's a parabola. It's hard to see here, but it's in the xz plane. There is no y component of it. A is equal to 0. That's the y component at 0. So it's a parabola that's opening downward because the square term is negative, opening downward there. So that's your standard old parabola in the xz plane. Here's this arm of it, the other arm is back there. It's a parabola there. But if a is some other constant, say, they say 2, then you're in the y is equal to 2 plane here. Never leaves that plane because it doesn't go anywhere else. It's in the y is equal to 2 plane. Well, that's the parabola here. Because then it would be ti plus 2j plus 2 minus t, 4 minus t squared j. That's, again, a downward sloping opening parabola there. Here's t is equal to minus 2. You're in that plane, the parabola there. T is equal to 4, a is equal to 4 or minus 4. They're always parabolas opening downward because that's always negative. But this R, which is defined by all of these, it would be anywhere in this shape here. All the A's in between 0 and -2, 0 and +2, 2 and 2, they would be here. So these would be this whole set of parabolas. So this is a good old hyperbolic parabola, okay? Your whatchamacallit function, saddle function, okay? The horse goes in here, your legs across here. It's a really steep saddle, okay? So I wouldn't want to sit down. No, okay. You can think of a parabola as the intersection of the vertical plane, y is equal to a. Whatever a you choose, that would be it, and then this contributes to here, this is here, but there's your constant, and that's why it's going up, because that's always positive, so your intersection in that plane is going up and up and up. When a is 0, then there is no intersection. It's just parabola down here. Okay. And here's Corey. So we're basically at 100% of anyone who's been here. One person's never been here, so I assume she's not going to go with the course. She's never paid, so I assume she's not. As a parabola, you can think of each parabola as the intersection of the vertical plane y is equal to a and the hyperbolic paraboloid no, I don't think I would have written it this way. Y squared minus x squared is equal to z. So here's your z, and if y is equal to a, then this would be y squared minus x squared, because that's your x, okay? And that would be that paraboloid, okay? And that's why it's hyperbolic parabola. Not sure I would have thought of writing it that way, but it's certainly true. Okay. Now, they're skipping example 6, so let's go back and see if we can do example 6 somewhere here. That's about the most white space we have. Let's see what we can do. Okay. Determine the intervals on which the vector-valued function r of t, vector r of t, we're on page 824, chapter 12, vector value functions, 12.1, vector value functions, example 6, right at the bottom of the page, very last example in the section, not on the slide set, so we're doing it, is equal to ti, I was in the Navy, that was Treasure Island, okay, there actually is such a place in San Francisco Bay, okay, plus, I'm stuck on my tag here, okay, plus the square root of t plus 1 j plus t squared plus 1 k. It says here again, determine the interval, this is a different sort of problem. Determine the intervals, or intervals, on which the vector value function is continuous. For this is continuous. Determine the intervals. Anyone want to hazard a guess?
So, it'll be -1. T's got to be greater.
Okay.
You can't have.
Right. Okay.
0.
Okay. You're zooming right at it. This doesn't have any limitations at all. This doesn't have any limitations at all. This is the only place, and what you have here is that t plus 1 has to be non-negative, so greater than or equal to 0. Subtract 1 from both sides, and you get t is greater than or equal to -1. You nailed it perfectly. There's the interval. If you want to write it in interval notation, you could write it as open bracket -1 to infinity. There is the interval on which this vector value function is continuous. It can't be continuous anywhere where t is less. even though that doesn't bother this or this at all, but you can't have anywhere where you have a discontinuity, so you have to have it. The J is your limiting component there, and you have to fit that, okay? They don't ask anything else. That's perfectly fine. Both F and H are continuous for all real numbers T. However, G is continuous only for T greater than or equal 1, so R is continuous only on the interval -1 to infinity. All right. Homework exercises 12.1. Any of the odds 3 through 9, they're all at Calc Chat. 3's at Calc View. Do number 11, it's both at Calc Chat and Calc View. Either 13 or 15, both at Calc Chat. 17 is at Calc Chat. Either 19 or 21, they're both at Calc Chat. Any of the odds 23 through 29, they're all at Calc Chat. 25's at Calc View. Any of the odds 31 to 37, they're all at Calc Chat. 31's at Calc View. 39's at Calc Chat. 41's at Calc Chat. 43 or 45, both of them are at Calc Chat. Any of the odds 47 to 53, they're all at Calc Chat. 51's at Calc View. Any of the odds 55 through 61, they're all at Calc Chat. 55's at Calc View. 63 should be at Calc Chat. Any of the odds 65 through 69, they're all at Calc Chat. 67's at Calc View. And then 71 through 75, they're all at Calc Chat. 71's at Calc View. You could think about doing 77 if you want to. Also explore doing 79 if you want to. They should both be at Calc Chat. 81 should be at Calc Chat. 83 and 85 are proofs. You can do those if you'd like. They should be given at Calc Chat. So even if you don't want to do them yourself, you can see how they do them. You can think about doing 87 if you want to, or 89 is a particle motion problem, so you're welcome to look at 89 as well. Now, I can't remember in which course. I know in one of my courses I've talked about, I can't think of her first name now, but her last name is Agnesi, one of the very earliest women mathematicians ever recorded, and she was quite good and came up with a curve that she studied a lot. And because of a terrible translation error, I think she was Italian, and they were translating either to or from Latin or to or from some other language, from Latin or from Italian, and they used the wrong noun in the translation. And it was supposed to be something like curve, and they used it which. I don't see how... And you can't tell me that wasn't a little bit of misogyny as well. They probably didn't like the fact that she had upped them on something, so they called that curve the witch of Agnesi. Shame on them. Okay. Any questions? 12.1. All right. Now let's move on to 12.2. And, Corey, if you're wondering why we didn't get any further than we have so far, we were also looking at, well, number one, I couldn't get my recorder to get started. It just sit there and spin and spin and spin and would never start. Finally, it suddenly did, so we were able to go. But we were also trying to look at the YouTube videos to see if they were actually working right, because Bill couldn't get them to work right. And it worked okay on mine, so it may be his computer. So that took a lot of the first part of the time, but I had to verify that indeed they had saved properly. And at least the first one did. So hopefully the others did as well. Let me know if you ever can't get access something that you think you should be able to. So chapter 12 still is vector value functions. Now we're going to look at differentiation and integration of vector value functions. We looked at continuity of vector value functions. We looked at limits of vector value functions. Now we're actually going to do some things that require both continuity and limits, differentiation and integration, and I think you'll find it's pretty straightforward. Hopefully just what you were expecting. If not, when you see it, you'll say, yeah, I should have expected that. Okay, so we'll first differentiate a vector value function, and we'll turn around and integrate a vector value function. So differentiation of vector value functions, the definition of a derivative vector value function parallels the definition of real value functions. Okay? The derivative of a vector value function R, notice, now they have the whole phrase here bolded, so you can't really tell the R is supposed to be bolded too, even if it stood alone. And this R prime, this is what the definition of the derivative of R is the limit as your delta t approaches 0, is R, that's a function R at t plus delta t, t's are scalar numbers, just a little bit beyond that, minus R of t, that's the difference of these two vectors divided by the delta t. That's dr dt. The R prime here is standing for with respect to t. For all values t for which the limit exists, okay? If R prime of t exists, then R is differentiable at t. If R prime of t exists for all t in an open interval I, then R is differentiable on the interval I, and differentiability of vector value functions can be extended to closed intervals by considering one-sided limits. Is that limit as delta t approaches, well, you would then go to the other form and say as t approaches c from the right-hand side or left-hand side, then you can consider closed intervals just as well. These are open intervals. They're a little bit easier to deal with because you don't have to worry about that endpoint.
Did you say the right-hand side, those scalars on the right-hand side?
Say that one more time.
I said, did you say the right-hand side, those scalars?
This right-hand side?
Yeah.
Okay, no, the t's are scalars.
Oh, okay.
But this, r's are vectors, but t's are scalar. So this is the derivative, the change of r as t is approaching 0. The change of r with respect to t as t approaches 0. That's what that is. This is a vector function. If r is a vector function, r prime is a vector function. Okay, but you're dividing by a scalar. The t's are scalars. Okay. So, differentiation of vector value functions can be done on a component by component basis. Just like just about everything you do with vectors, you're dealing component by component. When you're adding vectors, you add this component to that component, this component, that, you add similar components. Subtracting. Now, the multiplying, you have two different types of multiplication, dot products and scalar products. Dot products are components are multiplied together. Scalars, the cross product, you're going down those diagonals, so they don't quite fit. But integration and differentiation, or I should say differentiation and integration, component by component. Okay? And you say to see why this is true, consider R of t is some f of ti plus g of t j. Now remember that f of t and g of t are scalar functions, but their values are the components of the vector R of t. Applying the definition of a derivative produces the following. R prime of t, limit as delta t approaches 0, this is what we just said before, is R of t plus delta t, a little bit beyond t, minus R of t, so that's your change of R over your change of t, and that's what dr dt is. That's what this is. So if you expand this, this is f of t plus delta ti, this is g of t plus delta tj, this is f of ti, this is g of tj, but those are both minus, so those are minuses. Now, if you rearrange this ever so slightly, not so slightly, but f of t plus delta ti minus f of ti, put those together over delta t with the i's, and plus g of t plus delta t plus minus g of t over delta t j, this is just F prime of I plus g prime of tj. So what have you done? To take the derivative of this, just take the derivative of F, that's your I component, derivative of G, that's the J component, these are the components of your derivative function. R prime is F prime of Ti. So just do them component by component. No crossing, no cross products, anything else you have to worry with. Just do them component by component. The this important result is listed in the theorem shown below. Differentiation of vector value functions, R of t is f of ti plus g of tj. I don't know why sometimes there's these vertical lines in here. They don't mean anything. They're not in your book. I guess some graphic person put an extra key in. I don't know. Where f and g are differentiable functions of t. If they're not differentiable, you can't do it. Okay. But then R prime of t is alpha prime of ti plus g prime of tj. No product rules or anything else. You just take the derivatives of the scalar functions with their appropriate vectors, unit vectors. And if R of t in space is alpha ti plus g of tj, we'll take your tk. Take the derivative of that, alpha prime of ti, g prime of tj, h prime of tj. Okay. Note that the derivative of a vector value function R is itself a vector valued function. Okay? You can see from figure 12.8 here that R prime of t is a vector value, is a vector tangent to the curve given by R of t and pointing in the direction of increasing t values. So if this is your R of t vector here, and it's increasing as you're going in that direction, here is your R of t. Your R of t plus delta t must be somewhere over here. And then if this gets, as delta t is going to 0, this one gets closer and closer to that one until you have the tangent line. Because, okay, here's your R of t plus delta t. This is R of t. This vector here is the difference between this one and that. Okay? And then as the delta t gets less and less and less, this gets closer and closer to the tangent vector, which is at a single point, and that is the vector that is tangent to the curve and pointing in the direction of increasing t, which is exactly what a vector, what a derivative does. It is telling you what's happening as the top changes relative to the bottom. The top being your vector here, the bottom being the t plus delta t minus t. Okay, so here's example 1. For the vector value function, R of t is equal to ti plus t plus 2j, t squared plus 2j, find R prime of t. So let me get my pen set up. I thought I had it set up, but I guess not. R prime of t would then be what? I. That's yes in Navy speak, okay. Plus 2t j. There it is. Okay, then, thank you very much, sketch the plane curve represented by R of t and the graphs of R of 1 and R prime of 1. Okay, in 2 dimensions here. Let's start with R of 0 and plot it first. What would it be?
2j.
It's what?
2j.
2j, exactly. All right. 0i plus 2j. Okay, it would be right there. Okay. Your R vector would be from the origin to there. Okay. R of 1. Okay? 1I plus 3J. Wish I'd have done it a little taller, okay? Right there. So this would be your R of 1. This is the R of 0. This is R of 1. 1, okay? Okay? How about R of 2?
2I plus 6J.
Okay, that's 3, 4, 5, 6J. Okay, right here. Okay, so basically this is a half a parabola going in that direction. Probably was a full parabola going in that direction. Okay, it just depends on where you let your J start. Okay, so there is your graph. Basically, y is equal to x squared plus 2. That's it. I mean, if you let x equal t, then this would be, the y would be x squared plus 2, t squared plus 2. Okay, so there's your parabola. Now, let's do our r prime. Let's first do it at 0. What would be r prime of 0?
0.
It would be I, wouldn't it? Because it's I plus 2tj and t is equal to 0. So that'd be I. And sure enough, there it is. Unit vector in the positive I direction. Okay? And r prime of 1.
Plus 2J.
Okay. I don't know why that did, but it did. I plus 2J. That's a plus 2J. Okay? Well, let's plot it. It's right here. And it would be 1I 2J. It would be something like that. And sure enough, that's looks like it's tangent to the vector. It's a larger vector because it has I and J components, and the J component is larger. I forgot to write this. It's just I. Okay. So yeah, it's a longer vector, and it keeps on climbing. Okay, so there's your vector R of 1 right here, and there's your vector R prime of 1. Perpendicular, adjacent to, tangent to the curve at that point. All right, let me erase this scratch if y'all are okay with it. Okay, and let's see how they do it. Differentiate on a component by component basis to obtain x of, okay. From the position vector, you can write the parametric equations x equal t and y is equal to t squared plus 1. If you wanted to, they certainly are fine. Corresponding rectangular equation would be y is equal to x squared plus 2. They didn't tell you to do that, but that's certainly true, and we said it too. Okay. When t is equal to 1, then r of 1 is going from that one up there. I plus (3j), exactly what y'all said before, and r prime going from this one would be I plus 2j, exactly like y'all said. So it's just plugging in, and then it says to draw these. Moving kind of slow. I worked pretty hard, did a lot of walking and stuff, yanking and pulling this weekend. I've got my left knee so sore, it's hard for me to get up and down. So here's your R of 1, and there's your tangent R prime of 1. Now, they made this look a little bit bigger than what I did in mine. They aren't necessarily related very much at all, so don't expect them to be. Are they in the same direction? No, they're not. You know, are they the same length? No, they're not. Don't expect them to be. They're close enough. You might wonder that, but they're not. Okay. R of 1 is drawn starting from the origin to the position that it's going to be at t equal 1, and R prime is drawn at its initial point is at the value where R ends, okay, and then it takes off in the direction that it does. It's tangent to the curve given by R of t, pointing in the direction of increasing t values. Remember, your arrow was this way, that way, that way. No. So that was pointing that way. All right. That's example 1. Now, they've skipped example 2, so let's see, go back and do example 2. Almost guarantee you it's going to be a little more convoluted, don't you think? And sure enough it is. For the vector value function R of t, and that's equal to cosine ti plus sine tj plus 2tk, okay, find each of the following. R prime of t. Okay, want to do it? What would that be?
Negative sine t.
Negative sine t I plus
Cosine tj.
Cosine tj
Plus 2k.
plus 2k. Perfect. Okay. Just a second. Okay. Well, about this time, I don't know if it's because I'm leaning over here and the hot air is blowing up, but every time my eyes just start stinging. I don't know why. Okay, so we found the first one. The B part says, find R double prime of t. How do you reckon you do that?
Negative cosine t.
Yep, negative. You just take a derivative of R prime. Negative cosine ti minus sine
tj.
tj.
Plus k.
Plus what? 0k.
Zero.
Yeah, because the derivative of a constant is 0. Okay, now, basically, time out a moment here. What is this, if you remember? What is this? This part here, without that, describes a circle. Okay? You start with cosine 0, that would be 1, that would be 0, so you would start at 1, 0, and then when t is pi halves, then this goes to 0, and that goes to plus 1. So you're at 1, 0, and then it just goes around and around in a circle. This takes it off from the origin and makes that circle go like this. That's that good old helix, remember? Okay. The first derivative of that is the speed is going around that helix, and that's going to be minus the sine t plus cosine t plus 2. So it's always going to have a constant component here, but that keeps it in a circle, spiral, okay? But here, the second derivative, that's in a plane. So the second derivative is always just pointing inward. Okay, it's exactly the opposite of this, right? Okay, and that's it. It's in a plane, so we'll follow that up a moment. Okay, now let's do the C part. They tell us to. What is R prime dotted with R double prime? R prime of T dot product with R double prime at T, okay? Now, how do we do that? How do we do a dot product? Component by component. So we multiply these two components together, and what do we get? The I components together. What do you get? You're multiplying. Okay? So you multiply the signs, they go to positive, and that would be sine T cosine T. Then add to it the product of your next ones. And what would that be? Negative sine T cosine T. And then the Z component is 2 times 0, and that's 0. Well, guess what these add to? 0. Scalar 0, by the way, because this dot product gives you a scalar answer. Well, what does that tell you about these two? They're orthogonal to each other. They're perpendicular to each other, because anytime you have a dot product 0, that means those are. And sure enough, it is. This is a circular motion, but going along a helix, and the displacement vector is this way, the velocity vector is that way. Because it's circular, those are always perpendicular to each other, always. And the fact they're going up, that has a little bit of a tilt to it, but it's still, they're perpendicular to each other. Okay, how about this one? D, R prime of T crossed with R double prime of T. Here we're going to have to use our little old determinant matrix, you might say, modified as necessary. And that's I, J, K, I, J. Okay, what goes underneath that? Negative sine T. That's positive cosine T, because you're doing R prime. Yeah. And what's that, 2? Is that what you said? Okay. And then repeat the first two, just like we repeated IJ. Repeat the first two. Minus sine T cosine T. Okay. What goes next? Negative cosine T, negative sine T, 0, negative cosine T, negative sine T. Sorry. My writing's getting worse as time goes on. Okay, now what do we do? Your diagonals. I'll do the down diagonals first, and what you get on the first one? 0i. Do the next one, and what do you get? Minus 2 cosine T J. Okay, do the next one. Now, I'm pretty sure that's a minus sign there. I've drawn over it so many times I don't know why, but yeah, I think I put an equal there and it was supposed to be a minus. Let me make sure I'm right there. Yeah, I think I am. So that gives us what? I'm sorry? No, that's a J. K. And which is it? Plus sine squared t k, right? I can't get my k to right. Okay. Minus sine squared t k. Now we do our up diagonals. So these are always minus. What does that give you? Plus cosine squared t k. Next up diagonal. Minus 2 sine 2. No, that's a t. I kept getting lost there in my nomenclature. Negative 2. Wait, okay. Only that's a plus, isn't it? And that's an I. Okay, now why is it plus? Because your up diagonals are always minus, and this is minus a minus 2 sine t I. One more, and that's 0, because that's 0 down there. So it doesn't give you anything specific. So let's get them in the right order then. D, this thing would be 2 sine t I minus 2 cosine tj. And what's sine squared t plus cosine squared t? Plus 1k. Or plus k. That's all you have to put. Okay. Now, what does that do for you? I don't see anything in particular. Let's just see what we got. 2 sine t I minus 2 cosine tj plus k. Yeah, exactly what we got. All right. Now comes the next sentence that we got to before. Okay. Before we go here, I apologize. I've got to go get some water. My throat is so dry. I feel like I can hardly talk anymore. How much? We only got, what, 15 minutes? Can I make it? Let me pause. My throat's really... All right, this is the top of page 830 in Chapter 12, Vector Value Functions, and 12.2, Differentiation and Integration of Vector Value Functions. The parameterization of the curve represented by the vector value function, R of t is equal to f of ti plus g of tj plus h of tk, is smooth on an open interval I when f prime, g prime, and h prime are all continuous on that interval I, and when r prime of t is not equal to 0 for any value t in the interval. Okay? Now, why couldn't r prime of t be 0 for any value of t in the interval? Hang on to that thought, and I think we'll see why in just a minute. Okay? So, the That's all they do. They just tell you that. R prime of t can't be 0 on any value t in the interval. So find the intervals on which the epicycloid C, that's some curve C, given by R of t is equal to 5 cosine t minus cosine 5t I plus 5 sine t minus 5 sine 5t j. And this is a plane curve. It's not a three-dimensional. So there's no k component. And you're letting t go from 0 to 2 pi. And we want to find the intervals on which that epicycloid is smooth. It's sort of a broken up sentence, but that's what it is, where the epicycloid C is smooth. Okay? Now, what is meant to be smooth? The derivatives must all exist and be continuous, and the overall function R prime not equal to 0 for any t on the interval. Okay, so guess what we're going to do first? Take your derivatives, okay? Now, we don't have a k derivative, h derivative here because there's no h component. That's in 3 space, we're in 2 space. So we're just doing f and g here. So what's your f prime? Negative 5 sine t plus 5 sine 5t. Okay? And what is your g prime? 5 cosine t minus cosine 5t. I can't write, but there we have it. Now, what's required? That these be continuous. Sines and cosines are continuous everywhere. Okay, remember what the requirement is? F prime, G prime, we don't have an H, are continuous. They're continuous everywhere. Sines are continuous everywhere, cosines continuous everywhere. No problem there, okay? So is this smooth there? Well, there was one other problem, where R prime is not 0. So we must also have that there's no place where R prime, okay, R prime cannot be 0 for any value t in the interval, okay? So we have to have that minus 5 sine t plus 5 sine 5t cannot equal 0 at the same place where 5 cosine t minus 5 cosine 5t. They cannot be 0 at the same place. Now, let's see where those happen. Now, first thing we certainly can do is divide out the 5s. Okay, they're not contributing anything. So this says that sine t cannot equal sine 5t, right? And cosine t cannot equal cosine 5t. Is that right? They both have a plus and a minus. Yeah, okay. For different reasons, but they do. Okay? Now, where are the places where they would be equal? Now, if that was an even there, a 4t or a 2t, might be a bunch of them. But with 5t, there's not going to be that many where they're even. You know, they are equal. Where's one place they're going to be equal? At 0, certainly. So t cannot equal 0 because those would equal each other at both of those when t is equal to 0. So t cannot equal 0. Okay. Now, is there any other place where they might be the same? Okay. Where t is equal to 1? Let's think. Sine of 1, not necessarily going to be equal to sine of 5, so I don't think that would be it. The places I would investigate are your regular points, like your half pi's. So let's try that. What is sine of pi halves when t is equal to pi halves? Okay. Is that equal to sine of 5 halves pi? What you think?
No.
Okay. Let's see. Sine of pi halves is 1, right? Okay. 2 halves pi, 3 halves pi, 4 halves pi, 5 halves pi. It's a problem, isn't it, Houston? Okay. See, if we do something like pi quarters, there it's square root of 2 over 2, right? That's 1/4 pi, 2/4 pi, 3/4 pi, 4/4 pi, 5/4 pi. No, that's not going to be. Pi halves, I think, might be, it is 1. But it must also be there too. So let's do cosine of pi halves. Cosine of pi halves is where? 0. And then 2 halves pi, 3 halves pi, 4 halves pi, 5 halves pi, back down at 0 again. So yeah, they're equal to each other there too. Well, if that worked for those two, didn't work for the quarter pi's, what might be the next one? Remember, we're going from 0 to 2 pi. So might be the next place where you might run into problems. 0, pi halves. 3 pi over 2 probably. Let's try pi first. Okay? Well, not pi. So sine of pi is 0. That's 1 pi, 2 pi, 3 pi, 4 pi, 5 pi. Yeah, right at 0 again. Cosine of pi. Second? -1. Yeah, cosine of pi halves, or cosine of 0 is 1, pi would be -1. That's 1 pi, 2 pi, 3 pi, 4 pi, 5 pi, that's down to -1 again. So yeah, they're both 0 there. And then you said 3 halves pi, believe that's going to be the same too, because sine of 3 halves pi is -1, and sine of 15 halves pi, well, that's just going to be a bunch of times and winding back at the same thing for cosine. How about 2 pi then? Well, 2 pi is going to be the same as 0. So, yeah, I think we hit those. That'll be at pi at 0, pi halves, t can't be pi, t can't be 3 halves pi. And of course it can't be 2 pi again either. I'll write it down because it was included there. Okay. Now, everywhere else it looks like it can be smooth. and indeed it is. And let me erase my scratch here and see how they do it. Derivative of this, just like we got, okay? In the interval 0 to 2 pi, the only values of t for which r prime of t is equal to 0i plus 0j are t equals 0, pi halves, pi, 3 halves pi, and 2 pi. Now, they didn't tell us how they got them. I didn't tell you how I got them either. I just knew they had to be sort of those regular points, and we tested them. If you did this, produce this, what they call epicyclone, I believe is what it called, cycloid, epicycloid, then on the intervals between those two, 0 and pi halves, smooth, pi halves to pi, smooth, pi to 3 halves pi, smooth, and 3 halves pi to 2 pi, smooth again, everywhere except at those points. But at those points you have what I call cusps, okay? C-U-S-P, and there's more than one of them, so it's cusp. And that's where one derivative is one thing coming in, but a different thing going out. So definitely not smooth there, okay? And that's where it intersects the axis, okay? Now, frankly, I found that to be, and the other word for that, they use the term cusp also. They also use nodes, N-O-D-E-S. Of course, in physics, I think of nodes as something else, but we won't go there. And by the way, do any of you have physics right up to this? Huh?
I got physics 1.
Right up to this class? No, I mean today.
Yes.
You do, with Dr. Bryant?
It's at Jeff State.
Oh, okay, got it, okay. I'm sorry. I was going to say, if you had physics with Dr. Bryant, he's out today. He was in a pretty serious car accident on Thursday, and he's all banged up and just didn't feel like he could make it today and do much teaching. So I just wondered if he did, because I put a note on his board this morning. Okay. So, most of the differentiation rules in Chapter 2 have counterparts and vector value functions. Oh, wait, I'm sorry. In the figure, note that the curve is not smooth at the points when it makes abrupt changes in direction. Such points are called cusps or nodes, N-O-D-E-S. All right, and here are the properties of the derivative. And if they were true pretty much with scalar value, is it time? Is past time. All right, we'll pick up then on this slide next time. Homework exercises here will include, I think we got enough to do some. Any of the odds 3 through 9, they're all at Calc Chat, 5's at Calc View. Any of the odds 11 through 17, they're all at Calc Chat. And did we do higher order derivatives? I thought we did, but we'll wait. You can do a few more of those if you want, and we'll go from there. All right, good deal. So we did 12.1 to 12.2.